All right, cool. I'm Aiden,
I'm Tom,
and we're doing question 3.5.1.
and we are Group 7.
So we're group 7, and we're doing question 3.5.1. Consider the sequence of functions f sub j defined on the interval 0 and 1 by this equation. F sub j of x is x to the 1 over 2j. So for f1 of x, you get root x. For f2 of x, you get the square root of the square root of x, or x to the 1 over 4, and so on. Part A says, sketch the graph of f sub j for j is an element of 1, 2, and 3. f1 of x, as we saw, was just the square root, and that is a simple function that looks somewhat like this, where at 1 you get 1, and at 0 you get 0. Now, if you were to take a point such as 1 over 16, somewhere around here, and you were to take the square root of that, you would get 1 over 4, so that's somewhere around that. If you did that again, you'd get 1/2. So here we can say that 1 over 16 is somewhere around 1/2. And if you do that with every other point, you get a slightly larger curve like that. Now, f sub 3, you're going to take the square root of that again. So for 1 over 16, 1 over 4 is the square root, 1 over 2 is the square root of that, 1 over root 2, somewhere around 0.7 is the square root of that. So you'll get that somewhere up here for a 16th. And then again, it curves off towards 1. Here we can see our limit function, f of x. If we kept doing this for every f, we would eventually end up with the point 0, an open circle, and then just a line at 1. That is what we're tending to. Of course, that's not in our set, but that is the limit.
Oh, I'm just rubbing my nose there. Okay, part B says, does the sequence of functions fj such as j is in the positive integers converge pointwise? If so, what is the limit function? I'm going to slightly cheat here and just tell you what the limit function is off the get-go. We kind of already figured that out in part A. You can tell that it's going to converge to 0 at 0, because 0 to any power is still 0. And for any other value of x between 0 and 1, the square root being taken repetitively would just eventually end up being 1. So obviously for the definition of pointwise convergence, we've written on the board there to save us writing it now. For any epsilon in r greater than 0 and any x in the interval 0, 1, there exists an n such that this value here is less than epsilon for all j greater than or equal to n, where f is the limit function that we've just given you here. So what we need to do is show that that is true for this particular function. And the way we're going to do that is try and work out what n needs to be for this statement to be true. So for the case of x equal to 0, it's a trivial situation. 0 minus 0 is less than any epsilon you can choose greater than 0. So trivial situation is dealt with. So we'll just concern ourselves with x in the interval 0 to 1, not including 0. So in that case, what we will have is x to the 1 over 2j minus 1, because that's our limiting function to that interval. In this case, we want that to be less than epsilon. So this particular value here, because x is limited between 0 and 1, which we showed in part A, you'll see that that is actually equivalent to just saying 1 minus x to the 1 over 2j is less than epsilon. Okay, great. So what we can do here is just do a bit of rearranging, take the epsilon over to the left, x over to the right, and remember that we have chosen an x explicitly here, so x is a constant in this case. So we have 1 minus epsilon, take that over there, move the x to the 1 over 2j over there. Okay, and then the way to deal with this, we'll have to take logarithms. So if we take the natural log of 1 minus epsilon, which is positive, so we can do that, less than the natural log of x to the 1 over 2j. It still holds. And by the rules of logarithms, we can pull the 1 over 2j down the front. So we have natural log of 1 minus epsilon is less than 1 over 2j natural log of x. Okay, so it's important here to recognize that x is in the interval 0 to 1. And that means that ln of x is actually a negative number. So if we rearrange this, we will have to change the sign of the inequality. So what we will have is ln of 1 minus epsilon is greater than 1 over 2j. bring the ln x down over here. Then, from there, we're going to take the reciprocal, so we have to flip the symbols again, and that will leave us with j less than, I think, greater than, ln x over 2 ln 1 minus epsilon. So if we take any j greater than or equal to this particular value of j, then the original inequality will be true. So we can just simply, to make it an integer, say let n equal the ceiling of ln x over 2 ln 1 minus epsilon, and then just add 1 to be sure. And then that should satisfy the original equation. Just to clarify for the limit function that we chose, I suppose it's important that we actually justify why we did that explicitly. Consider that I'm just taking the limit as n goes to infinity of x to the 1 over 2 to the n. In the case of 0, again, like we said, it's trivial. 0 to any power will continue to be 0. With anything in the interval of 1, I suppose the best way to do it would be to take natural logs perhaps, but not absolutely sure. Anyway, ultimately what's going to happen is that this limit here, this power, sorry, is going to go to 0, because the limit as n goes to infinity of 1 over 2n, clearly is 0. So essentially x to the 0, anything to the 0 will be 1. So you know that anything that is non-zero will go to 1. And that's the justification for us saying that's our limit function.
Part C asks if the convergence of the sequence of functions is uniform. Now, from the pointless convergence definition that we wrote before, to make it uniform, all you have to do is move the x element of 0, 1 to the end of the definition. So you don't choose an x before, you show that it holds for x always after you've proved this. Now, I'm going to prove that it's not true. It is not uniform. The proof is rather intuitive. If you have your graph of your limit function, then for every j, you can draw another graph of the j function that comes up and approaches it. The definition of uniform convergence states that for every interval epsilon, the difference between the two functions is going to be less than epsilon, regardless of which x you choose. So, over here near 1, that holds. You've got your limit function and your j function that are pretty close together. But as you get closer and closer to 0, you'll notice that the difference between them increases until at some point your difference is more than epsilon. And so at this point and further towards 0, it no longer holds. The difference is not between epsilon, which means it is not uniform convergence.
Okay, so this is actually a pretty interesting question. Is it true that the limit of the integral of the function is equal to the integral of the limit of the function? Now in 281 we were told that that isn't true if the function isn't uniformly convergent. The correct way of stating that is that it isn't necessarily true if it's not uniformly convergent. Because we have a case here, we think, where it's not uniformly convergent, but this statement is actually still true. So I'm going to show you why that is. So we'll start with the left-hand side here. We want to take the integral of the function and then take that limit as j goes to infinity. So I'll just keep the limit over here for a moment. So the integral of our function would be the integral from 0 to 1 of x to the 1 over 2j dx. Now that is equal to the limit as well. I'm just going to write a squiggle because j goes to infinity, you know what it is. The integral here is quite simple. We just increase the power by 1 and then divide by the new power. So that will just simply come out as 2n over 2m plus 1. I suppose I should use j here, but that's fine. X to the 2n plus 1 over 2n between 0 and 1. Alright, so I apologize, I used n because that's how I did it when I did it the first time. Just imagine n equals j, so I'll write that down. Why is it 2n plus 1 over 2n? Because this would be 1 over 2n plus 1, which would be 1 over 2n plus 2n over 2n. And then that's just the same denominator, so it would be 2n plus 1 over 2n. And then this here is the reciprocal of that because you're dividing by the new power. So what will happen? If you take the limit as j goes to infinity, well, we're evaluating at 1 and 0, so this will just become the limit as j goes to infinity of 2n over n plus 1, 2n plus 1, sorry. Because the 0 term will still be 0, and then the 1 just becomes 1, so 1 to any power is 1, and 2n over 2n plus 1, you'll get that. So the limit as j, which is actually n, goes to infinity, should just be 1. Okay? Okay, on this side, we're a bit more interesting. We've got to consider that our limiting function was 0 at 0. I'll let you draw it, just so you can remember. So it's explicitly 0 at 0, but thereafter it is equal to 1 for anything not actually equal to 0. So how do we evaluate this? Because it's a discontinuous integral, so I tried looking it up just to reaffirm this to myself. It still feels a bit weird as the solution, but I think it's still true to say it, so let's just put a box around this. If we take the limiting function and we'll just ignore the 0 part, we'll assume it's 0, the integral is going to be 0, let's just ignore it for now. We could continue with an indefinite integral out this way, but it comes out to be 0, so just trust in that for the moment. If we consider the rest of it, the function is strictly just 1 for the limiting case. So we have an integral which is, and this is an improper integral because obviously we can't do this for 1, which is just 1 dx. So to actually make this correct, we should actually consider a limiting case. So the limit as t, which is just a dummy variable, goes to 0 of t to 1 of 1 dx. I understand I can just write dx, but I want you to see that there is a number 1 there, so that's what we're integrating. So what does that equal? Well, the integral of that is pretty straightforward. This can be done so long as the limit actually exists. So let's continue with it. You'll see the limit does in fact exist. So if that goes to 0, the integral of this, which is just x between t and 1. So that simply becomes the limit as t goes to infinity of 1 minus t. And of course, sorry, I said infinity, I meant 0. As t goes to 0, that just leaves us with 1. So, as you can see over here, we have 1 here, so the identity is actually true, even though you might want to think it's not.